Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from integrals, right? So in this lecture we are going to solve this important integral which is from 0 to 1, and the integrand is log x raised to n, where this n is a natural number, right? So n belongs to the set of natural numbers, and here we have logarithm of x, and here log x is the natural log, that is with base e, right? So we can also write log of x as ln x, right? But we'll prefer this notation, right? So let us start and let us see how we can solve this important integral with the help of gamma functions. So let us take this integral as I, right? And let us make the substitution as y is equal to log of x, right? So when we take y is equal to log of x, it implies that x is equal to e raised to y, right? Okay, now if we differentiate x with respect to y, then we have dx over dy is equal to e raised to y, right? Because the derivative of e raised to y with respect to y is e raised to y. So now we have dx is equal to e raised to y dy, right? So for this dx we have e raised to y dy, right? Now here the limits vary from 0 to 1, right? So when we have the lower limit as x is equal to 0, then the value of y can be obtained by taking x is equal to 0 in this relation. So when x is equal to 0, then y is equal to a log of 0, right? And log of 0, it tends to minus infinity, right? And similarly here when we take x is equal to 1, then y is equal to log of 1. So we have here log of 1 is equal to 0, right? So when x goes from 0 to 1, then y goes from minus infinity to 0, right? So now we can write this integral I in terms of y as minus infinity to 0. Then log x is replaced by y, so we have y raised to n, and dx is e raised to y dy, right? So now we have this integral, right? Now to move further, what we will do, we'll again make use of the method of substitution, right? So let us further substitute y is equal to say minus t, right? So when we take y is equal to minus t, then here we have e raised to minus t, right? So why we are making this substitution? Because we want to convert this integral into gamma function, right? So we have to take here y is equal to minus t. So dy is equal to minus dt, right? And let us change the limits accordingly, right? So here see y varies from minus infinity to 0. So now let us take t is equal to minus y, right? So when y is equal to minus infinity, or in other words, we can say that when y tends to minus infinity, then t tends to negative of infinity, because here we'll take y is equal to minus infinity, so that is positive infinity, right? So when y tends to minus infinity, then t tends to infinity. And similarly, when y is equal to 0, then obviously t is equal to minus 0, that is equal to 0, right? So now we can write this integral I in terms of t as integral. Here we have infinity, here we have 0. For y we can write minus t, and this is raised to n, and we have e raised to minus t, and for dy we can write minus dt, right? So now to neutralize this negative sign, let us interchange the limits, because we know that a to b f of say t dt is equal to negative of b to a f of t dt. So when we interchange the limits, then we put a negative sign before the integral sign, right? So we can neutralize this negative sign by interchanging the limits. So I is now 0 to infinity. We have minus t raised to n and e raised to minus t dt, right? Okay, now let us take this or we can rewrite this integral as 0 to infinity minus 1 raised to n t raised to n e raised to minus t dt. So now we can take this minus 1 raised to n outside the integral, and then we can write 0 to infinity t raised to n can be written as n plus 1 minus 1, right? And here we have e raised to minus t dt, right? So now we have written this integral in this form, and we can easily see that this integral is gamma of n plus 1. Now viewers, see gamma of n is defined as 0 to infinity t raised to n minus 1 e raised to minus t dt, right? So this is the Euler's integral. So gamma of n is defined like this: 0 to infinity t raised to n minus 1 e raised to minus t dt, right? And here we see that for this n we have n plus 1, right? And remember, n belongs to the set of natural numbers. So now this integral I is given by minus 1 raised to n, and here we have gamma of n plus 1, right? So the value of this integral is minus 1 raised to n gamma of n plus 1, where n belongs to the set of natural numbers. So viewers, we can also express this result as I is equal to minus 1 raised to n, and gamma of n plus 1 can be written as n factorial, right? Because when n is a natural number, then gamma of n plus 1 is equal to n factorial, right? So now we can write the value of this integral equal to minus 1 raised to n and factorial n, where n belongs to the set of natural numbers. So now let us quickly find out the values of these two integrals with the help of this result, right? So in this problem we have 0 to 1 log x raised to 4, and 4 is natural number, right? So the value of n is 4. So the value of this integral can be written with the help of this result. So we have minus 1 raised to 4, and then we have here 4 factorial, right? So minus 1 raised to 4 is positive 1, because this is even powers, and 4 factorial is 24, right? So the value of this integral is equal to 24. Now similarly we can find out the value of this integral. Here we have 0 to 1 log x raised to 10, and 10 is a natural number, right? So the value of this integral can be calculated with the help of this result. So we have minus 1 raised to 10, and here we have 10 factorial. Minus 1 raised to 10 is positive 1, and we have 10 factorial. So this is simply factorial 10, right? We can calculate the value of 10 factorial. Hello viewers, In today's class, we are going to discuss yet another important and very conceptual problem from integrals, right? So in this lecture, we are going to solve this integral using the concept of gamma function, right? So here we have to find the value of this integral from 0 to 1, and we have x log x raised to n, right? And remember here the logarithm is a natural log, right? So here the base of this log is e, which is the exponential number, right? So let us take this integral as I, and we'll solve this integral by making use of the concept of integration by method of substitution. So in this integral, the value of n, it belongs to the set of natural numbers, right? So this power n is a natural number. So in the first step, what we will do, we'll take a variable, say y is equal to a negative of log of x, right? So here I will make this substitution, right? So now when y is equal to negative of log x, then log x can be written as equal to minus y, and by definition of log, we can write x is equal to e raised to minus y, right? Okay, now let us differentiate x is equal to e raised to minus y with respect to y, right? So what we will get, dx over dy is equal to d by dy of e raised to minus y. So we have minus e raised to minus y, right? So dx can now be written as minus e raised to minus y, and here we have dy, right? Okay, now we'll change the limits. So here we see that the limits vary from 0 to 1, right? So when x is equal to 0, then here if we take x is equal to 0, then y tends to positive infinity, right? Because when x tends to 0, then log 0 tends to minus infinity, and here we have a negative sign. So we have y tends to positive infinity, right? And similarly, when x is 1, then we have y is equal to minus log of 1. So that is equal to 0, because log of 1 is equal to 0, right? So when x goes from 0 to 1, then y goes from infinity to 0, right? So now we can rewrite this integral I in terms of the new variable y. So now let us write I in terms of y. So we have here infinity, then we have 0 here, and x is replaced by e raised to minus y, e raised to minus y, and log x is replaced by minus y, right? So here we can write minus y, and we have the power n, and dx is equal to minus e raised to minus y and dy, right? Okay, now see, here we have minus y raised to n. So we can take minus 1 raised to n outside the integral, and then we have infinity, then we have here 0, and here we have e raised to minus ny, and then we have y raised to n, and then we have here a minus e raised to minus y and dy, right? Okay, now see, here we have an extra negative sign, right? Minus 1 raised to n we have taken outside the integral as such, and here we have an extra negative sign. So we can neutralize this negative sign by interchanging the limits, right? So we have minus 1 raised to n, so we can write 0 to infinity, because we know a property of definite integrals, that is a to b, f of x dx is equal to negative of b to a f of x dx, right? So when we interchange the limits, we put a negative sign before the integral sign, right? So here we have e raised to minus ny, then we have minus y, here we have minus y, and because the base are same, and here we have y raised to n and dy, right? So now we can write minus 1 raised to n, 0 to infinity, e raised to minus n plus 1, and here we have y, and then we have here n, and then dy, right? So now we have reduced this integral into this one by making this substitution, y is equal to negative of log x, right? Now we'll make another substitution here. It implies that we have to solve this integral by making use of the method of substitution twice, right? So now let us take another substitution. Say z is equal to n plus 1 y, right? So y is now z divided by n plus 1, right? And here we see that y varies from 0 to infinity. So when y is 0, then z is simply n plus 1 times 0, and here z is 0, right? And similarly, when y is infinity, then z is also infinite, right? And remember, here n is a natural number, right? So now let us differentiate z with respect to y. So we have dz over dy is equal to n plus 1, right? Because the derivative of y with respect to y is 1. And now dy can be replaced by dz divided by n plus 1, where n belongs to the set of natural numbers. So viewers, now let us express this integral I in terms of this new parameter or new variable z, right? So here we have minus 1 raised to n, then we have 0 to infinity, and when we take the variable z, the limits remains the same. So we have 0 to infinity, right? And here we have e raised to minus z, n plus 1 times y is z, and we have here y can be replaced by z over n plus 1, and here we have the power that is n, right? So here we have n, right? And dy can be replaced by dz divided by n plus 1, right? So now we have this integral. So let us simplify it. So we have minus 1 raised to n, and here we have 0 to infinity, e raised to minus z, we have z raised to n, n plus 1 raised to n, here we have dz, and here we have n plus 1 raised to 1, right? So now see, here the bases are same, so we can add the exponents. So we have minus 1 raised to n, 0 to infinity, then we have e raised to minus z, and then we can write z raised to n dz, and n plus 1 raised to n plus 1, right? So we can take it outside the integral. So we have n plus 1 raised to n plus 1, right? Okay, so now we have this expression, and let us apply the concept of gamma function to this integral. So now let us write this integral as minus 1 raised to n, n plus 1 raised to n plus 1. We have 0 to infinity, e raised to minus z, and z raised to n can be written as n plus 1 minus 1, right? Because this one and this one get cancelled. Why we have introduced here n plus 1? Because see, gamma of m is defined as 0 to infinity e raised to minus z and z raised to m minus 1 dz, right? So this is the famous Euler's integral, and this integral 0 to infinity e raised to minus z, z raised to m minus 1 is given by gamma of m, right? So if we compare these two integrals, then we can see that m can be replaced by n plus 1, right? So this integral now it takes the form gamma of n plus 1, right? So I can be written as minus 1 raised to n plus 1 raised to n plus 1, and here we have gamma of n plus 1, right? So viewers, the value of this integral is given by this expression, right? Now here we see that our n belongs to the set of natural numbers, right? So by definition, we can write gamma of n plus 1 is equal to factorial n, right? So we can replace gamma of n plus 1 by factorial n. So we have I is equal to minus 1 raised to n and n plus 1 raised to n plus 1, and here we have factorial n, right? So the final value of this expression or this integral is given by this expression, right? So now suppose we have to find the value of this integral 0 to 1 x log x raised to 4, then we can compare this integral with this one. So the value of n is equal to 4, right, which is a natural number. So the value of this integral can be obtained by putting n is equal to 4 in this result. So we have the value of this integral as minus 1 raised to 4, 4 factorial. Here we have 4 plus 1 5 and 4 plus 1 5, and minus 1 raised to 4 is plus 1. 4 factorial is 24 and 5 raised to 5 is 3125, right? So the value of this integral is now 24 divided by 3125. Now let us find out the value of this integral using this result. So this is 0 to 1 x log x raised to 3, and here if we compare this integral with this one, then the value of n is 3, right? And 3 is a natural number. So we can find the value of this integral by putting n is equal to 3 in this result. So the value of this integral is minus 1 raised to 3, 3 factorial, then 3 plus 1 4, then 3 plus 1 4, so we have 4 raised to 4, right? So minus 1 raised to 3 is minus 1, 3 factorial is 6, and 4 raised to 4 is 16 times 16, that is 256, right? So let us simplify it. So we have minus 6 over 256. So this is 2 3s are 6. Then we have 2 12s are 24. And here we have 8. Right? So the value of this integral is minus 3 divided by 128.